Okay, so having discussed the detection problem, the signal detection problems, we now move on to a discussion on the signal parameter estimation. And needless to say, parameter estimation is a very vast topic, and we'll be limiting our discussion to such topics which are of direct relevance to our course. And we will also be discussing only the estimation of such parameters about which we have no a priori information, in the sense we do not have any knowledge of the statistical distribution of the parameter to be estimated. Now, let's say that rather we will begin with an example, and a very simple example, just to drive home the point what exactly we mean by parameter estimation. Let's say that there is a parameter A to be estimated. This is the parameter to be estimated. And let's say, for our convenience, for the ease of discussion, and to make it easy to relate to, let's say that this is a voltage level. So let's say that it is a voltage level. Now, we receive a corrupted version of this. So the received random variable is the parameter to be estimated, which might have taken some value. It is, we assume that it's a voltage level for our sake of discussion. In this discussion, we assume it is a voltage level. So what we receive is A plus the parameter to be estimated plus the noise random variable as earlier. Now, suppose we have knowledge of this. Let's say we know the statistical distribution of this. Suppose we have this statistical distribution, we have knowledge of, say, Gaussian probably, or any other type of distribution. Suppose we have knowledge of the statistical distribution of the noise random variable, which is getting added to the parameter to be estimated. It is possible to form a density function like this, which is nothing but the density function of the received random variable, given that the parameter has taken a certain value. It is possible to develop this density function provided you have complete knowledge of the knowledge, in the sense the knowledge of the statistics of the noise random variable. So if we have it, it is possible to develop this density function. Now, for a moment, let us assume, it is just to carry forward the discussion, let's assume that A takes on, let's say the parameter takes on two values only, let's say plus 5 volt and minus 5 volt. It takes only two values, let's say. And as I said, we do not have any information on A, in the sense the statistics of A, that is, what is the probability of A taking different values. We don't have any information on that. So we will assume that it is going to take these two values with equal probability, 1 by 2 each. Now it is possible to, so again the problem here is to estimate what is the value of A. For the ease of discussion, I am assuming A takes on two values. Progressively, I will increase the number of values, and I will take it to a case where A can take a continuous set of values. Now it is possible to develop this conditional density function of the received random variable when A has taken a value of plus 5. So also we can develop, or we can have, the conditional density function of received random variable, given that A has taken a value of minus 5 volts. Now, if you have followed the discussion carefully with the help of the discussions we had earlier under the detection problem, you can see that the problem is now basically one of detection, because we have to estimate what is the value that A has taken, and A is going to take only two values. So if for convenience now I say that when A takes plus 5 volt it is hypothesis H1, and when A takes minus 5 volts it is hypothesis H0, I have a detection problem in my hands. So again, remember, I have simplified this now. I will take it, I will gradually increase the number of values which A takes on, and I take it to the case of continuous set of values. So now what happens is, it is possible, again from the previous discussions we know that it is possible to form a likelihood ratio like this. We can form a likelihood ratio like this, and since P0 is P1, we have assumed P0 is P1, we will compare it with 1. And if this is more than 1, we will say A is plus 5 volts. If it is less, we will say A is minus 5 volts. So we can see that in this particular case, when A takes only two values, the parameter estimation problem becomes one of detection, hypothesis detection, where one of the hypotheses is that A takes a value of plus 5, the other hypothesis is that A takes a value of minus 5. Now this can be written as simple rearrangement of the terms says that it can be written like this. Now what we are actually doing is we are comparing the two likelihoods. Earlier I had a likelihood ratio here. Now I have written the likelihoods on either sides of this, and I am actually comparing the likelihoods. Whichever likelihood is having the larger value, having received R, I plug it into these two likelihoods. Whichever likelihood has a larger value, I assume or I take that particular hypothesis is true, or in this context, whichever likelihood has a larger value, I say that A has taken that particular value. In the sense, after plugging in R in these two, let's say this turns out to be more than this, then I declare that A has taken a value of plus 5 volts. It can be wrong, as we have seen earlier, but this is how I can arrive at a decision here. This is how I can estimate the parameter in this particular example. So what you are looking at here is that there are two likelihoods, and we are finding out which one of the two likelihoods is maximum, and then taking a decision, or then arriving at a value for the parameter to be estimated. So this is the type of estimation technique that we are going to discuss further, and we aptly call it as the maximum likelihood estimation, or ML estimation in short, because we form the various likelihoods, and the one which is maximum, we take that as the value corresponding to that is taken as the estimate of the parameter to be estimated, as it is shown here. And that also gives me an opportunity to say, if I have not said that earlier, it also gives me an opportunity to say that the hypothesis detection problem, which would have looked like this, which would have looked like this if H0 and H1 were equiprobable. This decision rule becomes a maximum likelihood detection method, because again you are comparing the two likelihoods. Whichever is maximum, you are taking the hypothesis as that hypothesis, the corresponding hypothesis. So just to add to it, so whenever you are comparing likelihoods and arriving at a decision as to which of the likelihoods is maximum, that becomes a maximum likelihood detection rule, or a maximum likelihood estimation problem. Of course, there is more to this, but as I said, I am restricting to the concepts which we will be discussing in the course that we are learning here. Now, let's increase the number of levels that A can take. Let's say A takes on values now, say plus 5 volts, 0 volts, and minus 5 volts. So now it takes three values, three different values. Again, it is possible to formulate likelihood functions. We can form one like this, and then we have like this. This is the density function of received random variable given that the parameter A has taken plus 5 volts. This is the density function given that density function of the received random variable given that A has taken a value which is equal to 0. Then again we have for minus 5. Again, the decision rule would be, as by an extension of the previous principles, the decision rule would be the estimation would be like, to find out, having received R, plug it in into these three which you have already with you, plug it in these three, whichever is maximum you take that as the estimate of A. So by chance, if this time when you plug in R in this, you end up getting this as more than these two, you estimate that A is 0. If on the other hand, if this turns out to be more than these two, estimate A as minus 5 volts. So again, you can see that the basic decision mechanism, the basic method with which you arrive at an estimate of A is the maximum likelihood rule. So like you can extend this now, you can extend it, you can extend it to 4, you can extend it to 5 different levels, and you can extend it further and further till you end up getting a continuous range of values. When you have a continuous range of values, you can apply the maximum likelihood estimation. Again, remember, the maximum likelihood estimation rule is such that you find out that you estimate A as that particular value which maximizes the likelihood function, the various likelihood functions. So when you have A taking a continuous set of values, when you have A taking a continuous range of values, your likelihood function would be what we had earlier. It would look like this, simply like this. So for each different value of A, you get, for a range of values of A, you will have a number of likelihood functions. In fact, you will have an infinite number of likelihood functions for each value of A. Now, when A takes a continuous set of values, your maximum likelihood estimate of A would be, your maximum likelihood estimate of A would be that value of A which maximizes this likelihood. This is how the maximum likelihood estimation principle works. Now, with this elementary background discussion, we will take two examples and we will restrict to those two examples, because these are the two types of estimation problems which we are very likely to encounter in our course. The first example is one where we have a signal with us, because remember, in this discussion there was no signal involved, we had only random variables. So now we go for signal parameter estimation. Suppose we have a signal ST with us, and we have complete knowledge of the signal, in the sense we have exactly the time domain description of the signal with us, and let's say that signal is of a duration capital T, as it was earlier. We have a signal like this. Now we receive the received random process. What we receive is this signal scaled like this. So A can be considered as the gain, By the time you receive it, what is the gain? If the signal has dropped in strength, it is an attenuation. If it has, its strength has increased, it's a gain. So R of t, received random process, is A into St. Remember, St is completely described. You know complete knowledge of St plus the noise random process. Now we have to estimate A. We have to estimate the gain which the signal has experienced as when it has reached you. What is the amount of gain? This is to be estimated. Now we know that from our previous discussions, because those basic things we know that we can write this as equal to, where n can go to infinity. So the series representation we know about this. We know that it can be represented like this, and also we know that this term can be written as A S1 phi 1 t plus summation k equal to 2 to n A S k. So I have just isolated the first term and then of course the noise term. So we can also write it like this. Now again, from the previous discussion, we know that a convenient way to arrive at phi 1 would be to do this, where E is the energy of St. A convenience. So this becomes our phi 1 t, which means that we can write this as equal to A root E1 phi 1 t, root E1 phi 1 t, which of course implies that this is S1. I am just not going to the details because we have done this earlier. Probably in the previous two videos we have been discussing these type of problems. So we can write like this, and we note that since St is root E1 phi 1 t, root E1 being S1, S2, S3 onwards up to Sn are all zeros, which means that these will simply vanish. Again, to put in very simple words, in this summation we have only one term, which is A root E1 phi 1 t. And of course you have the noise terms over there. This is how it looks. Now this means that R1 is equal to, when you compare the coefficients, the received random vector, the first entry there, R1 will be A root E1 plus N1. The next one will be R2 equal to, this will be 0, it will be just N2. And then R3 would be N3, so on and so forth. And due to the reasons which I explained earlier when we discussed detection problems, these are not required because they don't carry any information in them regarding the parameter to be estimated. And remember, A is the parameter to be estimated. So the only random variable that you want to have with you from this set is R1. And since we have now only one random variable with us, we can drop this subscript. And our problem now, wherein we were supposed to estimate the value of A, becomes one where we have to estimate, or rather we have to estimate the value of A from the received random process, becomes a problem where we have to estimate this, out of which we already know the energy of S of t, because we know everything about S of t, so its energy also we know. So the problem now is of estimating A from this random variable, which becomes quite simple. Now, to proceed further, let's assume that n is n of t, rather the noise random process n of t is additive white Gaussian, zero mean, two-sided power spectral density n0 by 2, which means that this will be Gaussian, zero mean, and variance n0 by 2. Hence, I can easily form the likelihood as equal to root of 2 pi into sigma will be n0 by 2 e power. So this is zero mean, to this you are adding this, so the mean becomes a root e. So minus of r minus a root e whole square by 2 sigma square is n0 by 2. So we get the likelihood function, or you get the likelihood like this. And the maximum likelihood rule, decision rule, or maximum likelihood estimator says that the value of A, which maximizes this likelihood function, is the estimate of A. And we can easily see that this being a Gaussian distribution, the value of A, which will maximize this. What value of A is going to maximize it? The value of A that is going to maximize it is equal to, since this is the point where it takes its peak value, the value of A should be such that this becomes 0. So the estimate of A is R by square root of E. So how this works is that, having received the random variable R, having received a sample value of the random variable R, your estimate is equal to that received value divided by square root of E. To be more specific, if you receive 0.89 as R, probably 0.89 volts or whatever it is, if you receive it as 0.89, the estimate would be 0.89 divided by square root of E, depending on what is the value of the energy of the signal S of t. And an estimate is always, since it's only an estimate, it is always expressed with a cap like this. So there will be a cap on it. We'll put a cap on it to say that, to emphasize that it is an estimate. So this is how one can estimate the parameter A, which gets multiplied with a completely known signal, and when you receive that in addition to white Gaussian noise. So this is how the estimation rule works, and the schematics of the circuit which is going to do this would be like this. Receive R of t and you multiply that with the basis function, which is nothing but st divided by root e, and then integrate from 0 to t, sample this at t, that is the end of the integration, you sample it and pass the sample. So when you sample, you will get r, because r of t into phi of t. So what happens in this box is rt into phi t dt, which is nothing but r. So that r is here. When you sample it at the end of t, when the integration is complete, you sample it, you get r. And that r has to be passed through 1 by root e. And your estimate would be the output of this, which will be r by root e. So this is how it is. And this is the other equivalent realization would be, the equivalent realization would be with a matched filter, RT pass through a filter which has impulse response like this. This is the impulse response, and sample at t is equal to t, you get R, which you pass through 1 by root e to get the estimate as R by root e. Now in case you multiply with st and integrate, because st and phi t are just differing by a scaling factor. If you multiply with st and integrate, you will get rt, and st is nothing but root e phi t dt. That means instead of r, you will get r root e. So here it will be, instead of r, you get r root e, and the estimate would be, you have to multiply with 1 by e instead of 1 by root e, so that you will get root e into r by e, you get r by root e. The same thing applies here as well. If your matched filter is matched to st of t, st instead of phi t, you will have to pass it through, r has to be passed root er, that is the output of this filter has to be passed through 1 by e to get the estimate. So now we will take the next case. We will take the next case wherein we will estimate the phase of a sinusoid. We will discuss how the phase of a sinusoid is estimated. Let's say that we have received the received signal r of t is equal to cos 2 pi fc t plus theta p, and it is added, it is getting added by the additive white Gaussian noise of zero mean and two-sided power spectral density and 0 by 2. And let's say this is the interval, observation interval. Now the task is to estimate the phase. We don't know this phase, so this has to be estimated. This is to be estimated, and fc is integer times 1 by t. This is an assumption which holds good in digital communication. So fc is an integer times t. Now we can write the signal that we have here like this. It's a function of time, and also theta p is unknown. So we can now write this as and which can be expanded. We can use basic trigonometric identities and expand this as cos theta p cos 2 pi fct minus sin theta p sin 2 pi fct, and we can write here root of t by 2, and to compensate that we will write here root of 2 by t. Similarly, we do the same thing here. We put root of t by 2 here and we compensate that by writing it here. Now, if you observe this carefully, we can see that this is nothing but S1 phi 1t plus S2 phi 2t, where S1 is equal to root of t by 2 cos theta p, and S2 is equal to minus root t by 2 sin theta p. And of course phi 1t is equal to root of 2 by t cos 2 pi fct, and phi 2t is equal to root 2 by t sin 2 pi fct. So you can see why the this manipulation was done. It was done to make the energy of this unity so that we can call it as the first basis function, and similarly we can call this as the second basis function. S1 is root of t by 2 cos theta p, and S2 is minus sin theta p, root of t by 2, of course. So, and of course we know that these two are orthogonal to each other and they are of unit energy, which now means that we can write the received signal as equal to S1 phi 1t plus S2 phi 2t, that is the expanded form of this. We already know what is S1 and phi 1t, S2 and phi 2t, plus nt, which means that R1 is equal to integral 0 to t RT phi 1t dt, which gives, if you multiply this, because RT is this, I will not work it out here to conserve some space. Visualize RT is replaced by this, and then when you multiply with phi 1t dt, you will get the result as S1, because phi 1t into phi 1t, remember you are replacing this with this. When you multiply phi 1 with phi 1 and then integrate, you will get the result as 1 because it's unit energy, and S1 will come out, and then this term into phi 1t, when you integrate, you get the result as 0 because these two are orthonormal, they are sine and cosine, if you recall, and hence you will get S1 plus n1, where n1 is nothing but nt into phi 1t into integral 0 to t, and from our previous discussion we know that n1 will also be Gaussian because nt is Gaussian, white Gaussian, and two-sided power spectral density n0 by 2, 0 mean. So n1 will be 0 mean with a variance of n0 by 2, and it will be Gaussian. Similarly, R2 will be RT into phi 2t. By similar argument, we can write it as equal to S2 plus N2, where N2 will be independent of N1 because N of t is additive white Gaussian noise, and N2 will be identically distributed in the sense N2 will also be Gaussian, zero mean and variance N0 by 2. And now we can, if we can go further, we can see that R3 would be N3 because you are going to multiply RT with phi 3 to get R3, isn't it? And phi 3 being orthogonal to phi 1 as well as phi 2, we don't have to bother what is phi 3, but phi 3 is orthogonal to phi 1 and phi 2, which means that the result will be just N3. And by similar argument, R4 onwards, you will get only the noise terms. That means we can ignore R3 onwards, and we have to worry only about R1 and R2. We have to carry forward with us only R1 and R2 because this is the one which is going to help us in estimating the parameter theta p, estimating the phase theta p. Now we know that S1 is nothing but root t by 2 cos theta p, and S2 is nothing but minus root t by 2 sin theta p. So these are the two random variables that we need to have to estimate the parameter. These two are going to help us to estimate the parameter theta p. So now, and remember, they are independent, mutually they are independent to each other because n1 and n2 are independent. So I can write p r1 given the knowledge of theta p, pr1 given that theta p takes on a particular value is 1 by root pi n naught. It will be Gaussian distributed with variance n naught by 2 because you are simply adding this to get r1. Mean will be root of t by 2 cos theta p. So minus of r1 minus root t by 2 cos theta p whole square by n naught. And similarly, pr2 theta p would be plus because you are adding minus root t by 2 sin theta p with n2. So the mean will become minus root t by 2 sin theta p whole square by n naught. That n naught is 2 sigma square and sigma square is n naught by 2, which means that, so basically you have a random vector with you now with the components r1 and r2. So the joint PDF, the PDF of that random vector would be, they are independent to each other, so you can simply multiply them and you will get 1 by pi n naught, 1 by pi n naught e power. Now what we do is we will expand these terms and add them up because you are multiplying this. So in the exponents you will have the two terms getting added up, and since they are squared, we will square it, and then we'll get r1 square t by 2 cos square theta p and terms such terms you will get, and we'll simply add them. So I will skip that step because it's simple. It's a simple, though lengthy, it's a very simple step. So I'll skip that and I'll write the final result. You can verify it later. So minus t by 2 plus r1 square plus r2 square minus, so this minus is within this bracket, root 2t 2t under square root r1 cos theta p minus r2 sin theta p divided by, so the whole thing is inside the bracket and there is a minus sign here, divided by n naught. So you can see quickly that r1 square, the square of r1, then r2 square is here. T by 2 cos square theta p, t by 2 sin square theta p will add up to give t by 2, and 2 into r1 into root of t by 2 cos theta p gives minus root 2t r1 cos theta p, so on and so forth. So that's what you have here. So this is what we have, and by the maximum likelihood estimation rule, we know that by the maximum likelihood estimation rule, we know that the estimate of theta p is that value of theta p which is going to maximize the likelihood. This is the likelihood we have. This is the likelihood function. So the value of theta p is that value which is going to maximize this. So what we do now is we will operate with the log likelihood. So we take the natural log here because it becomes easier when you use the log likelihood here because of the presence of the exponential function here. We take the log likelihood and we will, when you take the natural log of this, when we take the natural log of this, you will get natural log 1 by pi n naught minus t by 2 plus r1 square plus r2 square minus root 2t r1 cos theta p minus r2 sin theta p divided by n naught. So this is the log likelihood now. So we have taken the natural log of the likelihood function. We took the natural log of this. Now remember, the maximum likelihood estimation rule says that the value of theta p is, the estimate for theta p is that value of theta p which maximizes this, because what maximizes this will maximize the log of this also. So the one theta p is the one which is going to maximize this. So we find that out by differentiating this. We find that out by differentiating this with respect to theta p. So the necessary condition is that the derivative of this with respect to theta p should become 0 at that value of theta p which is going to maximize this. So we differentiate this with respect to theta p, and we will end up getting, when we differentiate this, we will end up getting minus root 2t. You're differentiating with respect to theta p, so all these things are constants with respect to theta p when you see. So minus root t r1 sin theta p, and cos theta p, when you differentiate with respect to theta p, you will get a negative sign. So before that, probably this must be there. I left it out. Minus this bracket. This bracket is over here. So minus into minus plus root 2t r1 cos theta p. When you differentiate, you get minus sin theta p, and hence you get the result like this. And then you have plus root 2t into minus r2 into minus r2 sin theta p. You differentiate, you will get cos theta p. That means we can write this as minus r2 cos theta p, and this result has to be set to 0. That means the value of theta p which takes this to 0, which makes this 0, is the one which is going to maximize this likelihood, and hence that is the estimate. So 0, the value of theta p which makes it 0 is the estimate. This is how we can arrive at the estimate. This means, this says that So remember the value of theta p which makes this equation valid, the right hand side 0, value of theta p which is making this is equal to 0 is the estimate, the theta p cap. That's what is meant by this. That's what is meant by this expression. Now we can say that, of course, this is also not required. So we can now say that the estimate is minus tan inverse. So we can take it on that side, and I think it is R2 by R1. Anyhow, so this is the way we can estimate it, but there is a better way of doing this, a method which is probably easier to implement than taking the negative of tan inverse. So that is like this. So remember the key equation here, R1 sin theta p plus R2 cos theta p 0 when theta p is the estimate, or the value of theta p which makes this 0 is the estimate. So this is the key equation now. Now let us see what happens. So this is just, we are trying to develop an alternate way of arriving at the estimate, because this equation is the key equation. We have to reach this equation. We are going to reach this equation in some other way. So what we do is we will differentiate the result. Remember, t is the observation interval. We will differentiate the result of multiplying the received random process sample function with cos 2 pi fct plus phi, where phi is an unknown phase. So we will multiply RT with cos 2 pi fct plus phi, and then integrate the result from 0 to t and differentiate it with respect to phi. Now let's see what we get. We do this and we will get RT cos phi cos 2 pi fct. So I am expanding this minus RT sin phi sin 2 pi fct dt. And now I differentiate this with respect to phi to get RT sin phi. I differentiate with respect to phi, RT sin phi cos 2 pi fct minus RT cos phi sin 2 pi fct. We can differentiate this dt. We can differentiate, we can take the differentiation inside because the integration is with respect to t. So now we see that if we put root of 2 by t here and compensate with root of t by 2 here, similarly we put root of 2 by t here and compensate by doing this here, we see that sin phi can come out of the integration because the integration is with respect to t, and we will see that this, when you take sin phi out, we see that this, what stays back inside the integral, is nothing but RT into phi 1t, because we know phi 1t is root of 2 by t cos 2 pi fct. This is nothing but RT into phi 1t. Similarly, when you take cos phi root of t by 2 cos phi, when you take it outside, you see that what remains, you take it outside and include the negative sign inside, or rather you take this outside, and what stays back inside the integration is this, which is nothing but RT into phi 2t. because we know phi 2 is root of 2 by t sine 2 pi f c t. This means that, and rt into phi 1 t, if you integrate from 0 to t, you will get r1, and rt into phi 2 t, if you integrate from 0 to t, you will get r2, which means that this whole expression now becomes so now this expression will end up getting 0 to t r1. That integration is not required because the result of integration is r1. So r1, the result of integrating this, whatever is there within this blue boundary, the result of integrating that is r1. So r1 sine phi root t by 2 minus cos phi, and r2, yeah, so maybe we can write it in a better way, r2 cos phi. There was a mistake here which unfortunately I made at this stage, which I have now wiped. So rt cos 2 pi fct cos phi minus rt sin 2 pi fct sin phi. So when I differentiate with respect to phi, I had cos 2 pi fct cos phi. That would have become minus sin phi. So I think I dropped the negative. There was a negative sign here which I missed out. So the error is regretted. So I will not write it again. There is a negative sign here which I missed out. I have also put it as a pop-up in the video. When I was actually writing that, I made that mistake and I put it as a pop-up. Anyhow, so there is a negative sign here extra, which you might observe when you rework this. So this negative sign is there, which means the negative sign will be here as well. Now, what we see is that when we do this, when we multiply r of t, that is what the received sample function with cos 2 pi fct plus phi, and integrate it from 0 to t and then differentiate with respect to phi, we are indeed ending up getting this. We end up getting an equation which is similar to this. So now the estimate of the phase is that value of phi, which, so the value of phi which makes this result 0. Just as the estimate of theta p is that value of theta p which makes this 0, we can say that the phase that we are trying to estimate, remember the phase is hidden in this. In the received signal you have the phase. The phase phi, the phase that we are trying to estimate is that value of phi which makes this as equal to 0. So again, these terms are additional, and you can see that more appropriately. Now this resembles this. So remember, the value of phi which makes this as 0 is the phase we are trying to estimate. And we see that this can be now written as with a negative sign. But since we are equating it to 0 eventually, this negative sign doesn't matter. So this is the point now. So if we have this, because this is what we worked out to this, so if we have this, the value of phi which makes this 0 is the phase to be estimated, is the phase theta p which has to be estimated. So the value of phi which makes this 0 is the phase that we are trying to estimate, the value of the phase that we are trying to estimate. So this can be implemented rather easily in the following way. We can write this as equal to, probably I will write summation n0 to t by n plus 1 and integration n t naught to n plus 1 t naught rt sine 2 pi fct plus phi dt. We can write this process like this. So when n is 0, you integrate from 0 to t naught. When n is 1, you integrate from t naught to t naught to t naught. So we can see that the whole 0 to t is split into smaller intervals t naught, and the result is expressed like this, the same as this. And finally, when you have t by n here, t by t naught, I'm sorry, this n popped up from nowhere. Yeah, this must be the way. This is the way, correct. So when n is t by t naught minus 1, you can see that you will have the integration from t minus t naught to t. So you can see that the entire 0 to t interval is converted to small t naught intervals, and then the result is added up. So we can write like this, where of course t naught is also considered to be an integer multiple of, or rather fc is an integer times, so earlier we assumed fc is an integer times 1 by t. Now fc is also an integer time 1 by t naught. So we are splitting that interval t into smaller intervals in such a way that those smaller intervals are also connected to fc in this way. Integer times 1 by t naught is fc. Now we have a method to implement this. What we do is, we have received r of t, we will multiply it with the output of a voltage controlled oscillator. We will multiply the output of a voltage controlled oscillator, which gives out sine 2 pi fct plus some phase phi, which is not known, and rt is nothing but cos 2 pi fct plus theta p plus a noise sample function, and this result is integrated from n t naught to n plus 1 t naught, with n taking on these values. So we can start with n0. So it will integrate from 0 to t naught. The product rt into sine 2 pi fct plus phi is integrated from first from the interval 0 to t naught. The output would be called as an error value, an error function, not the ERF error function, some error output, and n stands for this index. So first you will get E0 here, and n, so when you start from your integration from 0 and end at t naught, you will get E0, and that we can sample at the end of the integration and give as a correcting input to the voltage controlled oscillator. So this will change the phase phi, and then again the next integration interval from t naught to 2 t naught will happen, and then you will get the next error signal, which will be sampled at the end of the integration and given back to the VCO, which will correct the phase further. Now this process will go on till the phase phi is such that the error signal is 0. Once error signal becomes 0, the voltage control oscillator's phase will be locked to that value, and that value, by virtue of this discussion which we had now, would be the phase estimate, that would be the phase estimate theta p. So this is how we can, this is the schematic of the phase estimation, maximum likelihood phase estimation. Yes, this is the schematic of the maximum likelihood phase estimation which can be implemented. Probably more easily than doing minus tan inverse R2 by R1. So with this we will conclude the discussion on estimation. We have discussed two types of estimation, parameter estimation, two types of parameters. One was the amplitude of a signal, S of t, which we did in the beginning of this video lecture, and now we have discussed the estimation of the phase. So this completes our discussion of detection and estimation theory from the perspective of the digital communication course that we are studying. So in the next video, in the next few lectures, we will discuss the various modulation schemes.